Hello, everybody. Welcome to the YouTube channel Numbers, Life and More. My name is Alex Surnov, and here is our third lecture of the course, which is dedicated to the interconnection between biology and mathematics. I will quickly remind you who I am. I have a PhD degree in experimental immunology. I'm a biologist, but I worked a lot with big data analysis in biology, with statistics, and to some extent with mathematical modeling. And I presume that the majority of my listeners also have some biological background, but they struggle to understand mathematics. And my goal is to remove this fear of mathematics, to familiarize you with mathematical concepts, and to make sure that next time when you talk to bioinformatics experts, you know precisely what they say, you know which questions to ask, and you know how to argue to them in case if you see that they misunderstand the biology matters of your mutual research. So previously, we have already discussed the concept of a real number and the functions defined for real numbers. We have discussed the notion of derivative and the integration. In the next lecture, in the current lecture, we will still have no biology applications or mathematical applications to biology, I should say, but instead we will continue discussing the foundations of mathematics. And now we will be talking about also functions as well as in the previous lecture, but this time those are going to be functions defined not for numbers but for points in multidimensional spaces. Don't worry, the spaces with higher dimensionality don't have to be visualized explicitly. You don't have to imagine them as they are. We will talk about them just in the language of formulae and expressions that one can draw or write on a sheet of paper. I will disclose a secret to you. Even professional mathematicians who work deeply in higher dimensional geometry or topology, they don't visualize, they don't imagine the spaces that they work with just inside their minds, inside their imagination. They also interpret them as formulae and work with them on a paper. No one can visualize the space with the number of dimensions that is greater than our conventional space that surrounds us with 3 coordinates. Our capacity, the capacity of us as human beings are just not sufficient to imagine spaces with higher dimensionality. But once again, this concept is extremely useful in various branches of applied mathematics. All the big data relies on multidimensional analysis and calculus and algebra. Just multiple other areas of mathematics which we may need, such as probability theory and stuff, also uses these concepts massively, and it's definitely important to know them. So on this I will finish the introduction and we'll start the video. Here is the list of references for the current course. It starts with the book on linear algebra and applications by the author with the surname Strang. It's a known book, pretty easy, which is pretty easy to read. So I encourage you to just get it somehow and have a look at it. Courant and John is the textbook of calculus, and it discusses things like derivatives and integration, also in higher dimensional spaces. So, and I have already mentioned that previously. So again, feel welcome to go deeper in these materials. Two more books are a little bit more specific, but for extended understanding of the topics that will be discussed today, those are quite useful too, and those are probably the best books that I know. So one is Novikov and Fomenko, Basic Elements of Differential Geometry and Topology, which studies the effects one can discover in the spaces that are curved, not only multidimensional, but also that are not Euclidean, with not straight angles in the coordinate grid. And another one is B.V. Shabbat, Introduction to Complex Analysis. In this context, the word complex is a rigid mathematical term, and it means a particular extension of the notion of real numbers. So the word complex doesn't really stand for something being complicated. It stands for discussing a particular entity that is called a complex number and functions defined for complex numbers. The book has two parts, one of which is present in English only in a sort of truncated version. Another one is it's fully translated, but I specifically selected this book because the version in which the first part is present in English contains only the necessary material, and it's pretty condensed with some irrelevant or maybe unimportant technical features being omitted. So for people who don't want to go really deep, I recommend this part 1 of this book, available at the webpage of Stanford University. We will start our discussion with matrices. And once again, just as in the previous lecture, I will have the table of content here. The chapter or the section that is just introduced will be highlighted in red and yellow. Then it will become gray, and gradually the contents table will be growing, delineating here the chapters that we have already discussed. Alright, so what are the matrices? A matrix is a rectangular table of numbers indexed with two indices. So here we have the number a sub 1, 1, a sub 1, 2, a whatever, all the way till a sub 1, k. The matrix has k columns and n rows, and these can be arbitrary numbers. There is an operation of transposition. The matrix in which the columns and the rows are split is called a transposed matrix, and I will be denoting as A superscript capital T. However, some other notations may be used in different other sources. So in this transposed matrix, the first column is just the same as the first row of the original matrix. The second column is the same as the second row of the original matrix, and so on. In addition to transposition, there is one more operation defined for matrices, which is very broadly used. and very useful. It is called matrix multiplication. It's a little bit a tedious concept. Let's study it from a simplistic example. Imagine first two matrices, one of which consists of only one row and another one consists of only one column. So those are particular examples of matrices. And more so, the number of elements in the first matrix, the number of columns essentially, equals to the number of rows in the second matrix. Well, in this case, the number of rows is just the same as the number of elements. How can we define the multiplication of these two objects, the product of these two objects? We simply multiply the corresponding elements to one another and then sum together the products according to this formula. All right. This result of this operation, further in, I will be writing for shortness in this form. It's like the multiplication of a matrix that consists of one row, the row indexed with 1, and the index of the column is just vacant, is formally denoted as a dot here. And another factor in this product is the second matrix that consists of only one column indexed as 1 and with the rows whose index is also vacant, whose index ranges from 1 to k. So that's going to be the short notation for the product of this kind. Now, let's extend this definition to the case of larger matrices. Assume that the first matrix now has multiple rows, but still the number of columns in it is equal to the number of rows in the second matrix. And here I highlighted different rows in different colors. The first row is in red, the second one is orange, although it may be not that distinguishable from red, and the last row is yellow, and the second matrix remains blue for now. How to multiply these two guys to each other? Well, we do the same thing as above, row by row. We select one row and the only column of the second matrix, and we construct a matrix of these products, this kind of products, taken so many times as there are the rows in the original left matrix, like this. We take the first row, multiply it to the column of the second matrix, write it as the first row of the resulting matrix. We take the second row, highlight it here, multiply it to the only column of the second matrix and write it as the second row of the resulting matrix, and so on. And in a compact form, this can be written like this. It's just the matrix that consists of only one column so far, whose elements are the products of the type that we introduced above. The multiplication of the first row to the second matrix, the second row to the second matrix, and so on. Now let's make the last logical step and see how to multiply matrices of different size so that the second matrix is no longer composed of only one column. Assume we have two matrices. One is n by k, n rows, k columns. Another one is k rows and m columns. So the important thing is that the number of columns in the first matrix must be equal to the number of rows in the second matrix. Otherwise, the multiplication will not work. And then what? What should we do? We should repeat the same operation as here, but then apply it to every column of the second matrix independently and essentially just stack them, stack the results horizontally in the output, like this. We select a row here and a column here. We write down the products of them according to the formula above, and we fill the output matrix with these products. This is the definition of the matrix multiplication, given that the number of columns in the first matrix is equal to the number of rows in the second matrix. That's how it looks. Let's pay attention to the fact that the multiplication of matrices is not commutative. The output will depend on the order of the factors in the product. A times B is not the same as B times A. What else can one do with matrices? Another useful operation applied to matrices is the computation of a determinant, but this can be applied only to square matrices. And the determinant is a number. The easiest way to think about it intuitively is in an iterative way. First, we define the determinants of a squared 2 by 2 matrix, matrix. If there is a matrix A, B, C, D, then by definition the determinants of it equals to A times B minus C times D. Now, what do we do to compute the determinants of a square matrix of the size 3 by 3? We, by definition, expand it this way. We first highlight the number A here, and we pay attention to the submatrix that is located to the left and down from the number A. Then we highlight the number B, and we compose the matrix of the two adjacent rows, and we exclude the two adjacent columns, and we exclude the elements of the same column to which the number B belongs itself. And finally, we highlight the number C, and we choose the matrix that is adjacent to it, like this. And then we write the weighted sum of the determinant of the three determinants of those three matrices. First, the matrix that is associated to the number 1, A, F, H, I. Then the matrix that is associated to the number B, D, G, F, I. And finally, the matrix associated with the number C, taken with different signs and different weights. The weights are actually A, B, and C, and the signs are going like one after another, first plus, then minus, then plus again, and that's it for now. That's how we define the 3 times 3 determinant from the 2 times 2 determinant that has been already introduced. And then, iteratively, by induction, we can define an arbitrary determinant of the size n times n. If we have an n times n matrix formally shown like this, we can reduce it to the weighted sum of the determinants of a lower order. For example, in this case, we highlight the number a. We associate this right bottom matrix to the number a and write the multiplication of them. I mean, the product of the number itself and the determinants of the associated matrix. Then we write the minus sign, take the number b, and compose the matrix of dh and other columns except for the column that the b belongs to, and of course except for the row that b belongs to, which is shown here. So the column that is composed of e and h is just crossed out. It doesn't belong to this matrix. Then we put the number, the sign plus, choose this the third elements of the first row and associate a matrix to it, and then we flip the numbers as many times as we have the summands here, plus minus, until eventually we hit the number c. We associate the matrix to it, which is located in the bottom left corner of the original matrix, and we close the definition on this. That's how we reduce the n times 2 determinant to the n-1 times n-1 determinant. Then we can expand that one further, and we reduce it to n-2 times n-2 determinants, and so on, until we eventually hit the 2 times 2 determinants, which we introduced by definition previously. A determinant is a very, very rich concept. Not only it is used almost everywhere in algebra, in statistics, and big data, but also it has a number of exciting properties and symmetries which we don't have to discuss right now. They're not that relevant for us. But whoever is interested, just pay attention, Google for it, read the books that I recommended. It's worth investigating which juicy properties determinants have. And we will, of course, return to this concept again and again later on. Another operation matrices can be subjected to is inversion, and actually pseudo-inversion for the sake of precision. Before talking about them, we first have to introduce the identity matrix. It's a square matrix, necessarily square matrix, whose elements are all zeros except for the elements of the main diagonal, which are all ones. It is usually denoted as capital I or as capital E. I will stick to this notation here, capital I. And once again, it's called the identity matrix. So let's examine two cases. The case number one is if there is a square matrix A, then it may have an inverse matrix. And if it has one, then the inverse matrix is uniquely defined. What is the inverse matrix in this case? It is such a matrix that is just denoted as a to the power -1, such that the product of the inverse matrix and the original matrix equals to the identity matrix. If such a matrix exists, the inverse matrix, if it exists, then the flipped product also equals to the identity matrix. So it doesn't matter whether to multiply A by the inverse A or inverse A by A, the result is the same. And the inverse matrix exists if and only if the determinant of the original matrix is non-zero. And here is the value of determinants. One of its great features. It's sort of the measure of inversibility. If it's non-zero, the matrix is inversible. If it is zero, the matrix is not inversible. It doesn't have an inverse matrix. And why it is called a to the negative 1? Well, later in the same lecture, we will see that the inversion of a matrix has sort of the same meaning as the inversion of a real number, as computing, like for the number a, computing 1 over a if a is non-zero. The same way we can compute the inverse matrix if its determinant is non-zero. The second case is if a is not square necessarily, then the so-called Moore-Penrose theorem holds. For any matrix A, maybe non-square, maybe not inversible, a pseudo-inverse matrix A plus exists. It is such a matrix that if you multiply the original matrix A by this A plus and then by A again, the result will be A. And if you multiply A plus times A plus, it's going to be A plus. So informally, it kind of gives you an intuition that the product of A and A plus, or A plus and A, doesn't do much with the following factor. It's not a strict claim, but it helps you to see that it's indeed a sort of a generalization of the inversion of a matrix. And also there are the properties 3 and 4 that also must be satisfied. The product A times A plus being transposed is just the same as A times A plus, as well as A plus times A being transposed also doesn't change, stays the same, if all elements of the matrix A are real numbers. Both the 3 and 4 hold strictly when the elements of A are real numbers. So far we haven't discussed any other type of numbers except for real numbers, but later in this lecture we will, and then a certain modification will be required for this pseudo-inverse definition. However, so far for real numbers it holds as it is written here. And the last comment in this context is that we will talk about pseudo-inverse matrices much more in the lecture on big data analysis, because they are there quite often. They are seen there quite often. Everywhere where you deal with large tables, yeah, it's natural to operate pseudo-inverse matrices. All right. Well, let's go to the next topic right now. So we talked a little bit about matrices. Another key player in all this multidimensional science is the concept of vectors themselves, and the coordinate plane, coordinate grid, just coordinates as such. The coordinate plane is composed of two real axes. One is denoted as x, another one is y, and the whole collection of points that belong to this plane is denoted by this bold capital R, which we already are familiar with. That's the symbol for just the space of real numbers. But squared. Squared essentially means that there are two coordinates. The elements of this space are points on a plane. They have two numbers associated to them. The projection of the points to the x-axis and the projection of this point to the y-axis. That's an obvious duality. A point can be represented as a pair of numbers, as well as every pair of numbers can be represented with a unique point. The structure composed of these two arrows, two lines, and the point of origin is called the frame of reference. And now, please appreciate the following sentence. It's important. It's crucial, however, not many people who are not specifically involved in this math really think about it and really keep it in mind. If you change the frame of reference, if you stretch, move, rotate the whole that structure composed of the two arrows and the intersection point between them, then the coordinates of the given point A will change. So by changing the frame of reference, I mean that the point A stays at its position as I am highlighting it here. And just the entire frame of reference can be moving somehow, moving or stretching or shrinking. So depending on how you move it and how you modify it, the x sub A and y sub A coordinates of the points A will change, and they will change in a strictly defined way. The way how they change under this coordinate transformation is crucial for defining vectors formally in the course of differential geometry and linear algebra and stuff. We will be talking about vectors more visually and will not really go into this technical definition, but at least keep in mind that the essence of vectors has something to do with the way how these objects modify their coordinates upon the transformation of the coordinate grid. Okay, so where can we use the coordinate plane? I have two examples. Obviously, you can use it to define the position of points on a plane, just as here, but it may not only be a plane. It can be the surface of the Earth. It can be any other two-dimensional surface, maybe curved, maybe bent, maybe it's going to be a surface of a donut. Regardless, if you have two independent coordinates, you can use this two-dimensional notation to locate the points. You can also use this two-dimensional notation if you are considering 2 points on the same line, and one point has the coordinates, one point is x, another point is y. They have coordinates x sub, they have the coordinates x and y along the straight line on which they live. And here the combination of the points x and point y is useful to be thought of as a point A, capital, in a higher dimensional space. That's it. That's what I mean by showing x sub A here and y sub A here. So the point A is kind of a combination of x and y examined together. Now, how do we think about vectors? A vector is a segment of a straight line equipped with the notion of direction. Essentially, it's a little arrow which has a defined beginning, a defined end, and the beginning and the ends are not interchangeable. So the vector is directed from the beginning to the end. But also, there is an obvious duality between vectors and points. Not unique duality, but at least every point on a plane can be represented with a unique vector that starts in the origin and has its ends in the corresponding points. This vector is called a radius vector, but essentially in mathematics they are just easily substitutable with one another. So if one says a point, it automatically means that one means a vector. The length of this vector, just according to the Pythagorean theorem, is nothing else than just the square root of the sum of squares of the coordinates of the points, as shown here. And the length of this vector is usually also denoted with those straight brackets as the absolute value and as the determinant in terms of matrices. So for vectors, this writing here essentially just means the length. If we have 2 points, there is a unique vector associated to each of them, and the distance between those points is also computed according to the Pythagorean theorem as this formula. It's the square root of the sum of squares of the differences of these points, of their coordinates. Nothing complicated. So the distance between the 2 points here is denoted as r sub AB, or alternatively it can be the length of the vector B minus the the length of the vector A minus the vector B in this case. What can we do with vectors? Well, we can apply arithmetical operations similar to those we have introduced already for real numbers. We can add and subtract the vectors together, just as I told you already in the previous slide. So you have a vector A and we have the vector B. The sum of those vectors is gonna have coordinates just which is a coordinate-wise sum of the previous vectors. The new the coordinate x of the sum is going to be the sum of the x coordinates of the input vectors. The y coordinates of the resulting vector will be just the same as the sum of the y coordinates of the input vectors. And in a matrix term, it's written here. Pay attention that we write the vectors as matrices that are composed of only one column. Just the same notation as we already introduced for matrices. It applies to vectors as well. A vector is a collection of numbers. If you write them one under another, it's going to be a valid description or valid representation of a vector. You also can multiply a vector with a constant scalar number, constant real number, as shown here, and then this operation applies to each coordinate independently too. So essentially it means that the vector, the input vector, just gets stretched c-fold if you multiply it by c. The x coordinate becomes c-fold stretched and the y coordinate becomes c-fold stretched. Before talking about another operation one can introduce for vectors, let's make a quick digression and we discuss the notion of linearity. There is a little bit of ambiguity, a little bit of discrepancy. By definition, a linear operation A is such an operation which, once being applied to a weighted sum of two arguments, returns the weighted sum of the output of this operation being applied to each argument separately. That's the linearity by definition. And if the arguments x and y are real numbers, then the only operation that satisfies this property is actually just a multiplication by a constant number. The function f of x, that by definition equals to a constant number mu times x, satisfies this property, and that's the only form of the function that satisfies linearity. Okay, so that's the linear function by definition. With a minor comment to it, I consider here only the regular axioms accepted by a canonical mathematics framework. Sometimes, if you're curious or just randomly, you can encounter online certain discussions about other functions being linear, which cannot be written in this form mu times x. But if you go deeper, every such discussion relies on some additional axioms which do have some strange consequences, some counterintuitive consequences indeed, the so-called choice axiom. But it's too deep matter which I don't want to really touch now, and for biology it seems to be irrelevant. However, so what is the digression that I want to talk about here? Despite this is the definition of linearity, the function f of x equals a times x plus b, where a and b are fixed real numbers, is also called a linear function. Despite that it does not formally satisfy this property anymore, but it is called a linear function informally, just simply because its chart is a straight line. Okay? But in terms of vectors, usually we're gonna talk about the linear transformations by definition. So the linear transformations that for which this property holds. Okay, once this is clear, and by the way, if an ambiguity arises, I will specifically comment what I mean by saying that something is linear. Okay, once this is appreciated and thought through, we'll continue to another operation that one can do on vectors. And this operation is going to be nothing else than linear operators. So what is a linear operator? It's a transformation of the input vector A that satisfies the property of linearity that I introduced in the previous slide by definition. What is it? If you have an input vector A with the coordinates x sub A and y sub A, then its linear transformation is going to be the weighted sum. So how to say it? The coordinates. So its linear transformation is going to return a vector, first of all. The coordinates of this output vector are gonna be the weighted sums of the coordinates of the input vector. The coordinate of the vector lambda a, which is the output of the linear transformation lambda, is going to be p times x sub a plus q times y sub a, where p and q are the fixed numbers, and the y coordinate is computed in an analogical way. How to write it down more concise? We can represent the linear transformation lambda as a matrix of p, q, t, and s, and then by multiplying this matrix by the original vector a, we will obtain exactly the output vector that is shown here in this picture. The matrix p, q, t, s is called therefore the matrix of the linear operator. And this is one of the ways how matrices can be used. So essentially, a matrix is a representation of a linear operator on vectors. It is not the only way how a matrix can be used. Sometimes matrices are used for other reasons with other whatever in other formalism, but using matrices as a representation of a linear transformation is definitely one of the most common ways of using matrices. And here comes an example. For example, we have the vector A. In order to turn it by the angle theta counterclockwise and simultaneously stretch it gamma fold, one has to multiply this matrix by that vector. This matrix will apply the same transform to every other vector around. It will rotate the input vector and stretch it gamma fold in both directions, in x and y to the same extent. Not every linear transformation has a matrix that is expressible in this form. A linear transformation has 4 elements. Here we have just 2 independent variables within this matrix. So an arbitrary linear transformation stretches x and y coordinates not proportionally, not to the same extent. But as I already showed, the arbitrary linear transformation is just defined by an arbitrary matrix. What is going to happen if we want to apply 2 linear transformations at the same time, one by one, sequentially? Then we have to subject the input vector to the multiplication of the 2 matrices one by one, but the order matters. If we have one transformation defined by the matrix P, Q, T, and S, and another one defined by the matrix U, V, W, and Z, then first we can apply the first matrix, the first transformation to the original vector by multiplying the matrix by this vector, and then we can subject the output of this transformation to the second transformation by multiplying the matrix associated with the second transformation to the output vector. The matrix multiplication has a good property that you are free to rearrange the parentheses. So if you have this expression, you are allowed it can be proven. You are allowed to first compute the product of these two matrices and then apply the transformation that is associated to the product of the matrices to the original vector. It's going to be just the same thing. But what you are not allowed to do in general case is to put the first matrix before the second one. So since the multiplication of matrices is sensitive to the order, you must specify explicitly which operation, which linear transformation you apply first and which one the second. Linear operators will become quite useful in the next slide. However, before we transit to the next slide, we have to first familiarize ourselves with Cartesian coordinates. It is just basically the same thing as we already talked about. It's the vector A, and it has the two coordinates x sub A and y sub A. But a representation of these coordinates is slightly different now. We interpret the vector A as the weighted sum of two other vectors. One has the coordinates 1, 0. Another one has the coordinates 0, 1, and they are shown here. These vectors are called the basis vectors, and the weights in the weighted sum of these two vectors are essentially just the coordinates of the original vector. That's the Cartesian representation, dated back to René Descartes, a French philosopher of 17th century, I think. He introduced that coordinate system first, and essentially it's just the same coordinate system as you probably observe in these central districts of large towns, where you have rectangular blocks and streets intersecting each other at straight angle. So once we once we have this Cartesian coordinates picture in mind, let's talk about the thing, the operation that somehow closes up and summarizes the previously introduced concepts. It's the dot product. For now, we will introduce the dot product only in Cartesian coordinates. A broader definition of it will be given later in the end of this talk. But in Cartesian coordinates, assume we have two vectors of the same length, A and B, with their coordinates, and then we introduce an operation that takes both of them as an input and returns a number. This operation is denoted in different ways. It can be written either as A dot B, and there is how the name dot product appears, or it can be written as A comma B in parentheses, or in this structure. I prefer to use this notation, the angular brackets with a separator between the inputs. And also the dot product is sometimes called a scalar product. So computation of a dot product is a two-step process. First, you take the vector A and you convert it into, like, from being a one-column matrix, you convert it to a one-row matrix. Such an object is called a covector. After that, you use this covector as a linear operator and act with it on the second vector of our pair, on the vector b. And you obtain this formula, which is the sum of the products of the corresponding elements of the two vectors, as it's shown here. The covector A appeared at step 1, acts on the vector B. The dot product has a numeric value. It's a number after all. Its value is equal to the product of the lengths of the input vectors times the cosine of the angle between these two vectors. We still will remember that all these vectors, in case of Cartesian coordinates, are interpreted as growing from the origin. These vectors are fully determined by their endpoints because the beginning of each of them is fixed at the origin, and that's a good property of Cartesian coordinates. Now, whether or not this operation is symmetric. It is symmetric. The dot product of A and B is the same as the dot product of B and A for those vectors whose components are real numbers. And once again, later we will introduce complex numbers. For them, this formula also needs a certain modification. But for real numbers, this formula holds. Okay, so now let's just make a deep breath in, a deep breath out, and summarize what have we studied so far. We learned the matrices, the vectors, operations on vectors, how these operations are connected to matrices. We imagined the structure called the 2D space. It's a coordinate plane. And what? Well, and we just learned the operations applied to these objects. Now it's time to think about vectors the same way as we thought about real numbers in the previous lecture, and introduce the functions that act on the vectors on the an arbitrary dot in a two-dimensional space, and we will see whether these functions have similar properties to those functions that we already talked about. Let's transit to another part of the lecture. So here is the coordinate plane, x and y, with two coordinates. To every point on that plane, we define a certain number, a value in a real number space, which we will call f of x and y. It's a mapping that sends R2 to just R. The visual representation of this mapping can be a two-dimensional surface, as shown here. So above every point on a coordinates plane, there is a point, a dot marked, whose vertical coordinate is just the value of the function f of x and y. What can we do with this function? We can differentiate it if it's smooth enough. Well, potentially we can differentiate. The derivative may not exist, but there is no conceptual problem with differentiating some of these functions. But the derivative must be computed along a certain direction. A derivative is something which is one-dimensional. So it's not just possible to transfer this this concept to two-dimensional spaces with no modification. In order to compute the derivative of this function, you essentially can compute two values. You can fix the y coordinate and interpret the function f of x and y as a function of f of x with y being constant, and differentiate this function. It's going to be the derivative in this direction. And also you can fix x and differentiate this function along the y direction. Every other derivative in other direction will be a weighted sum of those two. And the way how to write these derivatives is shown here by using such roundish d signs. That's the partial derivative sign. And the whole expression here is called the partial derivative of f with respect to x and with respect to y. We can differentiate these functions with slight modification, but we can. We can also integrate them, and the integration is pretty much the same as we already introduced. We discretize this function, the same as we introduced in the previous lecture. I must be repeating it all the time because some viewers will be, there will be viewers who haven't yet seen the previous one. Actually, I encourage you to go back and to watch the first lecture, the second lecture. Anyways, we can discretize the function f of x and y by splitting the coordinate plane into these facets and considering the value of the function being constant in each facet. Then we sum together the volumes of those bricks and just send the size of each facet to 0 while keeping the whole plane tiled with them, so while tending the number of the facets to infinity. If all the regularity constraints that we discussed in the previous lecture holds, so that the limits of this operation doesn't depend on the actual splitting of the plane to facets and actual choice of the particular points within each facet to compute the constant value of the function in it, then the function is called integrable, and the integral is essentially just the volume below, let's say, between the surface defined by the function and the coordinate plane, the same way as in the one-dimensional space. However, there are more different integrals designed specifically for the two-dimensional and three-dimensional cases, and for the cases with greater dimensionality. In order to discuss them, we first want to dive a little bit into the topic of vector fields. Vector fields are very popular in physics, and you will see why in a second, but also they became recently popular in biology for describing cell motion, for describing morphogenesis and differentiation of cells in the space of gene expression. And essentially what a vector field is collection of vectors growing from every point in the space. So to every point in the space there is a vector associated, like on this picture, x-axis coincides with just the surface of the Earth, and y is the vertical axis. And then in every point of this space there is a vector pointing downwards and approximately constant in its length. You know what it is? It is gravity. It's just the force that attracts the apples from the tree to the ground. As you see, there is a vector growing from every point in the space, and only one vector growing from this point, from each point. Here is another example. It is flow of liquid or a flow of gas. We choose a particular point, an arbitrary point. There is a particle of the liquid in it, and this vector that is associated to this point is nothing else than just the velocity of this part of liquid. And this particle is moving into the space, moving in this space along the tangent curved line, along the curved line tangent to the vector field, to the velocity field. This particle would move this way, this particle would move this way, this particle will move this way. A similar thing is applied in three-dimensional case. Here is some sort of a tornado, and again, the orange line is the trajectory of a given particle of dust or a given particle of air, and the velocity vectors are tangents to this trajectory in every point of it. Here is a little bit of a caveat. We so far have built our theory only for the vectors who start growing from the origin, who are fully defined by their endpoint. And when I define a vector field here, what I essentially write? I define it as a vector with coordinates u and v, whose coordinates are themselves the functions of the coordinates of the input points. So in this point that I'm showing, there is the coordinate x and the coordinate y. We plug these coordinates into this function, and the function returns the corresponding coordinates of the vector, of the output vector. But it means that this vector also grows from the origin, because we haven't specified explicitly the beginning of this vector. We would probably need to write down not 2 coordinates but 4 coordinates of this vector of u and v. However, in case of Cartesian coordinates, it's not necessary. We agree, or mathematicians agree, for simplicity, that all these vectors can be parallelly transferred into the origin, and we can talk about them just the same way we talk about the input vectors, as being fully defined by their endpoints. We can do it in Cartesian coordinates. It's just regular rectangular coordinates. It's a plane space. It is not curved. Therefore, the vector is not going to get changed when parallelly carefully transferred with the preservation of its length and with the preservation of its angle that it forms with the coordinate axis. This little trick, the parallel transfer, allows us to still describe the output vector, the vector field, as only 2 coordinates, but not as the collection of the endpoints coordinates and the beginning points coordinates together. In case of the spaces with curved coordinates, this trick will no longer hold in general, but there are its own tools to simplify the notations. And in the end, the procedure with the parallel transfer is intuitively valid, because we don't lose any information. We still indicate explicitly for each vector which input points it corresponds to. We define the vector uv as the function of the coordinates x and y. And we know exactly that this value of u and v is specific to this position in x and y space, and the other pair of values is specific to another position. So I hope I explained it right. Just once again, the vector field is a vector function defined in every points of a space, but it's written in a vector notation as a matrix that consists of only one column. That's it. I think that's the most digestible formal definition of a vector field. Now, another example, the fourth example of a vector field is the gradient. Why am I talking about the gradient here? For two reasons. First of all, because I have already discussed it a little bit in the previous slide. It's the vector that is composed of the two partial derivatives of a given function. And secondly, because it's extremely useful. Because everywhere, like in machine learning, in all kind of optimization problems, the gradient is going to be appearing again and again, and we will talk a lot about it. At least we will mention it a lot. How does it behave? How to think about the gradient? It's a vector field. Well, technically speaking, it's a covector rather than a vector, but in Cartesian coordinates it doesn't matter. The difference between vectors and covectors becomes evident in curved spaces, and maybe we'll touch on it a little bit. But for the Cartesian case, it can be interpreted as a vector field, which is, as I said, composed of the two partial derivatives, and it points to the direction in which the function grows the most rapidly in this point. So in this point here, in the center of this hump, the vector vanishes because the function doesn't grow here. It's flat. I mean, it has its peak here. On the slope, although, it grows, and the direction to which it grows the most rapidly is straight towards the middle of the hump. Therefore, the gradient is non-zero. It's visible as a little arrow here, and it points towards the hump. And again, at the margin here, the function almost doesn't grow again, and the vector almost vanishes too. But the largest length it has near to the, how to say it, on the slope of this larger hump here, where the function grows the most rapidly. That's how to think about a gradient, and once again, we will hear these words many, many times. All right, now, once I introduced vector fields, let's talk about those specific examples of integrals that differ from the definition that we already have given, and differ from those from that integral that we discussed one lecture ago. So multidimensional integrals. Here is one example. Imagine that we have a function f of x and y defined for just a two-dimensional plane, and we draw a path on the input two-dimensional plane. Here is the path. And it's a valid operation to compute the integral of the original function along this path. So we neglect the surface that is defined by this function. We just cut it off and erase it. And we isolate only this fence, only the values on the functions, only the values of the function above the drawn path. And the integral in this case will be just the area of this fence as shown here with those vertical lines. So that's one example. Another example is an integral of a vector field over a path. We have a vector field, we have a trajectory of a particle which is not associated to this vector field anymore. It's just another particle. The vector field is not the field of the particle's velocity. The particle just moves somehow by itself along the orange trajectory. And we want to compute the integral of the dot product of the particle's velocity and the external vector field. So for every point on a path, we compute the tangent vector to this path. It's going to be the particle's velocity. We dot multiply it to the background vector field, and then we integrate this number, which is just a real number, along the path. And finally, there is yet another example. It's the flux of a vector field. So here is the vector field. Here is a closed contour with a certain surface stretched across this contour. And we compute the dot product of the vector field and the vector that is orthogonal to this contour and has the unit length. And we integrate this value, this number, essentially, over the whole surface that is stretched across the contour. That's yet another example, the flux. It's essentially the measure of how much of the vector field flows through this contour, nothing else. What I forget to say previously is that in the three-dimensional space specifically, there are some unique operations introduced, namely cross product and curl. They don't have direct analogy in the spaces of higher dimensions, but in this hydrodynamics and in air dynamics, they're quite useful in electricity theory as well. But I don't think we will really use them in biology, honestly speaking. And a minor addition here to this slide is that although I say that these integral types are somewhat different from what we previously studied, I must once again emphasize that they are also so-called Riemann integrals. It's in order to define them, we don't have to develop another concept of integration. We don't have to modify the notion of integration as such. It's not the same as what I commented in the last lecture about Lebesgue integral or Ito integral. No, the concept of integration, the technicality of integration is just the same here as in the previous lecture, and the same as on the previous slide. It's just another way to apply this integration type, actually. Yeah, I think enough said about that. And now, once we already discussed just single numbers and points on a plane, we can easily generalize our knowledge to a space of arbitrary dimensionality. Essentially, one number is just one coordinate. A point on a plane, which is a two-dimensional number kind of, is a pair of numbers, pair of coordinates. And a point in a multidimensional space, which is denoted as capital bold R to the power n, simply is represented as a column of numbers whose there are as many as there are coordinates in the space. So n-dimensional space is just the points in an n-dimensional space is just a collection of n numbers written stacked like this as a matrix with just one column, or as an n-dimensional vector. The operations on these vectors are similar to those introduced for the coordinate plane, and the dimensionality of space is, as written here, the dimensionality of a space, n in this case. What is it? It is the maximal number of linearly independent vectors, which means such vectors that are not representable as a weighted sum of other vectors. In a two-dimensional plane, you have two vectors which cannot be expressed one from another, the vertical vector and the horizontal vector. Any other vector can be represented as their weighted sum. In a three-dimensional space, any arbitrary vector can be represented as a weighted sum of the longitudinal, and the vertical vector. But those three cannot be represented from each other. This concept is used to define dimensionality of an arbitrary space. In this context, it's convenient to examine what a curved space can be. So here is an abstract picture of a space which is not straight. The coordinates here are not Cartesian. And we immediately notice that parallel transfer is not so obvious anymore as written here. Indeed, if we specify two vectors in a point in this space, these vectors will no longer dwell in the space itself. They will belong to a tangent plane or a hyperplane, multidimensional plane, associated to the given space in the given points by definition, because vectors are segments of a straight line. Straight line cannot belong to a curved space. Straight line can belong to a linear space only. In order to transfer these vectors here, we have to invent a particular procedure that maps these vectors that belong to this tangent plane associated to the space in this point to another pair of vectors that belong to another tangent plane which is associated to the same space but in another point. It's not a difficult procedure, but it's a tedious procedure. It is a procedure that requires precision and a thorough understanding of what you're exactly doing. I don't think I'm gonna go deeper into this right now, but just appreciate this idea and keep in mind that curved spaces may contain some hidden obstacles of working with them. Now let me give you an example of curved space. The simplest, I guess, example, and also pretty widely used, is polar coordinates. What is it? It's essentially replacing the x and y of the original plane by phi sub a and r sub a, which is the length of the radius vector of the point and the angle between the x-axis and the vector associated to the point. It means that x and y are replaced by some nonlinear functions r and phi according to this trigonometric formulae, and they can be reconstructed, x and y, again from r and phi. Well, unless it's the origin. In the origin, phi is not defined because of this. So this illustrates that the curved space is described by replacing the original coordinates by the functions, which are nonlinear, the functions of the original coordinates. Instead of having x and y, we have now r and phi, which are nonlinear with respect to x and y. Polar coordinates. Polar coordinates. The polar bear is waving to you. It's just an emotional digression in order to make the information a little bit more digestible. So what is left there? What else should we study today? We want to learn how the concepts that we already discussed can be applied for solving problems. For example, for solving equations. There was a reason why I introduced all these vectors and determinants and operators, right? I introduced them for a purpose. I need some of them to work for solving equations that may appear in practical applied computations. Before talking about this, let's remind ourselves what the linearity is. Again, the linearity property claims that an operation A, once being applied to the weighted sum of two arguments x and y, is equal to the same weighted sum of the outputs of this operation being applied to each argument separately. Just let's memorize that. And now let's talk about linear equations. The simplest linear equation involves just real numbers, a, x, and b. And given a and b, the problem is to find x. And there can be two cases. Case number one is if a is not equal to 0, and then the solution is trivial, x just equals b divided by a. The case number two is if a is equal to 0, and then there are two subcases. Either b equals to 0, and then x can be whatever number, because any number multiplied by 0, by a, will give you 0. So a is arbitrary. X is arbitrary in this subcase. Or, another subcase, b is not equal to 0, and then there is no solution, because there is no such number that can be multiplied by 0 and give you a non-zero output. In the same framework, we will now talk about the equations written for vectors. SLAE, systems of linear algebraic equations. Assume we have a system of two algebraic equations, linear, with two unknown numbers, x and y, with the coefficients alpha, beta, rho, tau, sigma, and mu being just fixed numbers. how do we find x and y from here? Well, like trivially, we express first y from x using the top equation. Then we substitute the expression for y into this bottom equation. We combine the corresponding summands together, and we find x from the linear equation that appears here in the bottom. This is the formula for x. And finally, we substitute this value for x into the formula for y that we derived previously, and therefore we get y. If we have an n-dimensional set of equations with n equations and n unknown values x1, x2, all the way to xn, we can apply the same framework as here in the top row, but the computations, of course, will become more and more bulky as the number of equations grows. However, this way of writing these equations can be useful for practical purposes, but it's too lengthy. And for theoretical study, it's better to use matrix notation. We have, let's have a look. What specifically do we have here? We have the matrix A, which is n by n, which is composed of the values a sub 1, 1, all the way to a sub n, as written here. This is the expression for the matrix A. And we have the vector B, which stands in the right-hand part of this equation. And we have the vector X, composed of x sub 1, x sub 2, etc., all the way to x sub n. And the equation is just the product of the matrix A and the vector x equals to vector B. Here the product of the matrix and the vector is just understood in the same manner as the product of the matrix and the matrix that consists of all that consists of just one column and n rows, as well as the B. B has the same shape. So in which cases this equation does have solutions. And here we recall the same two cases and the same two subcases as we have already discussed. If the determinant of the matrix A is non-zero, then x can be relatively easily found just by inversing the matrix A and multiplying it by B. If the determinant is indeed equal to 0, then there are two subcases, just the same way as in the previous slide. Either some of the equations are derivable from one another, so they're redundant. They kind of encode the same information as here. So assume that the first equation is alpha times x plus beta times y equals to sigma, and the bottom equation is just the same, but multiplied by rho, where both sides of the equation is multiplied by rho. Obviously, these two equations are redundant. They encode the same information. If this happens, then there is an infinite number of solutions in plural, and x can be chosen arbitrarily, and y will be dependent on x using that formula above here. So the solution to this set of equations is just a straight line encoded by this set of constraints. Or, alternatively, the second subcase, if the equations are not equivalent to each other, and they encode different information. Like here, for example, we have the equation alpha times x plus beta times y equals to sigma on the top, and in the bottom we have a row times alpha times x plus beta times y on the left hand side. But now it is equal not to rho sigma as in the first case, but to tau sigma, which is not equal to rho sigma. And then the system is inconsistent. Then it means that these equations cannot coexist, right? They would be coexisting, they would be consistent with each other in the upper case, but in the lower case, in the bottom case, no. In this case, there are just no solutions at all. No x and y can satisfy these constraints, and this feature shows a great importance of determinant. It dictates whether or not the matrix A at all has an inverse matrix, and also it indicates whether or not the linear system of equations can be solved, whether it has solutions and how many solutions it has, either just one if the system is well posed, or infinitely many if the system is degenerate but consistent, or no solutions at all if the system is both degenerate and inconsistent. Well, do you remember that I said that a matrix can be viewed as a linear transformation applied to vectors? Let's pose the following question. Given the matrix, which vector will remain the same up to the length? Maybe it's going to be stretched, but which vector will remain pointing to the same direction once being treated with a linear operator, with a matrix? Formally speaking, consider a linear operator A that maps Rn to Rn, and assume the following equality holds for a certain vector u and a certain number lambda. Matrix A times the vector u equals just the same vector u stretched lambda fold. Then the vector u and the number lambda are called the eigenvector and the eigenvalue of A, the operator A, respectively. Eigenvectors, and so that prefix eigen in German stands for proper. It's like a proper value of this matrix or this operator. And these objects are gonna be extremely useful in various applications in data science, in essentially everything that relies on linear algebra, in the tools of manipulating large tables, computing some, I don't know, well, some variants of correlation scores and stuff. So eigenvalues, eigenvectors, inverse matrices, pseudo-inverse matrices, we will need this all in data science quite heavily. So how to find eigenvectors and eigenvalues? We start with the former equation. A times u equals lambda times u. U is a vector, A is a matrix, lambda is a number, and A is a square matrix, obviously. What we do first is moving lambda u from the right-hand part to the left and taking u outside the parentheses. After this, the only thing that remains in the right-hand part is going to be just 0. And in the left-hand part, there is going to be what? This factor in the parentheses is a matrix, It's a, which was here previously, minus lambda, which moved from the right hand part. But we cannot just subtract lambda from a, because lambda is a number and a is a matrix. We have to convert lambda into a matrix as well somehow. And the way how to convert it properly is to multiply it by the identity matrix of the same size as a. You can just write down carefully all the coefficients of all matrices here manually, and make sure you understand that this equation here is equivalent to the first equation on top here. It's just the same equation. And then let's think what we can say about lambda from this new equation. We first recall this analogy between the linear set of algebraic equations and just a simple algebraic equation a times x equals b, where a, b, and x are numbers. So there is a duality. Well, not duality. There is an intuitive correspondence, intuitive share of properties. Let's talk about this way. Between the equation matrix A times vector u equals vector b, and I highlighted that u and b are vectors by putting those little arrows on top of them, and the basic simple linear equation a times x equals b. Assume x here is non-zero, we know it, but we know that b is 0. The only way how to ensure that a times x equals to 0 is to demand that a itself is equal to 0, since x is not 0. The same way here, if we know that u is non-zero, if we know it by the condition, but we know that b is 0, then the only way how this equation can hold is if the determinant of the matrix A is 0, as we just discussed in the previous slide. So, from having this equation, we can claim that the determinant of this matrix must vanish, must be 0, in order to be able to produce the 0 output when being applied to a non-zero input vector. So we need to find lambda from this equation now. The determinant is a number, it's good, and in this particular case it's 0. We have to expand the determinant based on the formula that I introduced in the very beginning of this talk. This is going to be a very long sum of certain products, and in each of them there can be not more than n copies of lambda multiplied by each other, because in the end the determinant is the combination of the products of different elements of the rows and the columns of the matrix, and there are just n rows and n columns in the matrix A. So this determinant is an nth order polynomial of lambda. We can find its roots. We can find its roots explicitly if n is smaller than 5, as I discussed in the previous lecture. And in case of greater n, we can use some numeric approaches and find these roots with a computer. It's computationally a little bit expensive, but modern computers do it just fine, very quickly. And then we find several roots of this polynomial. They all will be eigenvalues to the matrix A by definition. And then for each of them, let's say lambda sub k, each of these numbers we can substitute in the original equation and find u. Well, in case of a simple two-dimensional case, if we know one of the lambdas, and yeah, we don't know u, but we know the components of the matrix A, obviously, we substitute it here. We find lambdas. Here is the expression of lambdas from the formula of the roots of the quadratic polynomial. Then we use this value of lambda found here to identify the components of the vector u. And from the top equation we can extract that the second components of u is proportional to the first components of u with this factor. Or equivalently, we can extract this formula from the bottom equation. It is the same. This formula that links together the first and the second components of the vector u, and this formula that links together these components is really the same, just because lambda itself is not an arbitrary number, but because it is found from this equation, and it already has components of the matrix A in it together. So there is another bit of information in this equation. So one way or another, you can use either the top equation or the bottom equation. It will result in the same proportionality between the first and the second components of the vector u. And then every vector which has this proportionality between its components can be claimed as an eigenvector of the matrix A associated to the particular eigenvalue lambda. So every individual eigenvalue has a collection of vectors, infinitely many eigenvectors, which all are parallel to each other, which all differ from each other just by stretching. But their first components and their second components are coupled to each other by a strictly defined proportionality coefficient here. Okay, so we found first lambda by equalizing the determinant to 0, and then we use this lambda to identify u up to the precision of proportionality, of linear stretching, proportional stretching. That's it. However, here is a caveat. What if the polynomial, this equation here has no roots? And by the way, this polynomial is called the characteristic polynomial of the operator of alpha. Of A, of the matrix A. But it may have no roots, just the same as this polynomial here has no roots. This polynomial is x squared plus 1 equals 0. It never intersects the horizontal axis, never vanishes, this orange curve. What happens in this case? So let's discuss that. For this, we will have to introduce complex numbers. You probably already have heard that complex numbers is something dealing with the square root of -1. However, a more logically consistent way of introducing them is by considering a pair of real numbers, just regular real numbers, x and y, organized in a pair, an ordered pair, first x then y, with its own name, Z, and inventing an artificial rule for multiplication for these pairs, such that if there are two pairs, x comma y and a comma b, then by definition the product of these two pairs is going to be another pair of the same kind with the components x times a minus y times b and x times b plus y times a. We know how to represent a pair of real numbers on a plane. Let's do it. Let's represent z as a point on a plane where the horizontal coordinate x has a Cartesian basis vector just simply called as 1, and the vertical Cartesian basis vector is called I. They both have the same length, and why is the vertical one is called I? Well, just because. This number, the complex number z, has two components x and y, which is the projection of the representing points of this number onto the corresponding axis. And also it has two other characteristics, namely its polar coordinates, introduced just the same way as we already introduced polar coordinates above somewhere, some slides ago. It has the length of its radius vector, r, and phi, which is the angle between the radius vector and the horizontal axis. Now, from this definition of the multiplication for the complex number. Oh, by the way, yes, the plane itself, in case of complex numbers, is called C, capital bold C. So the rule of multiplication for complex numbers demonstrates a peculiar property. If you multiply the complex number 0, 1 by itself, or multiply two copies of this number, then the result, just according to this definition of the multiplication, the result is going to be the number that is minus 1, 0. And using this notation here, that z equals to x plus iy, well, here must be 1 times x plus iy, essentially, but no one writes 1 in multiplication. So from using this notation, one can convert this formula here into another formula, an equivalent one. 0 plus 1 times I times also 0 plus 1 times I equals to negative 1 plus 0 times I, which essentially means that I squared equals to negative 1. This is the correct, consistent way to introduce complex numbers and to deduce from this definition that I squared is equal to negative 1. Another concept associated to complex numbers is complex conjugation, and it's just the same complex number as the original one, but reflected with respect to the horizontal axis. So instead of being x plus iy, it's x minus iy, and it's denoted as z bar. Complex numbers have a number of advantages, which we will discuss on the next slide. Much of mathematics becomes simpler, more closed, and more elegant when you talk about complex numbers and not only of real numbers. I will enumerate 4 features of complex numbers that are extremely advantageous. It's the fundamental theorem of algebra, holomorphy of functions of complex numbers, the link between exponential and trigonometric functions, and also that the space of complex numbers forms the broadest extension of the space of real numbers, which still represents a field, which still forms a field. Now let's discuss each of these points individually a little bit. Fundamental theorem of algebra states that every polynomial has at least one root. And that's very important for us in context of searching for eigenvalues and eigenvectors, as I discussed. So when we extend our attention to the field of complex numbers, the question of what to do if the characteristic polynomial of a given operator has no roots doesn't make sense anymore. It must have at least one root. And in particular, the polynomial x squared plus 1 equals to 0 has two roots, positive I and negative I, namely. Next, holomorphy of the functions. Well, one can define functions on complex numbers, and one can also define the procedure of differentiation, the concept of derivative for such functions. And these functions seem to behave better than their counterparts in real analysis, in real calculus. For example, in the previous lecture, I showed you an example of a function for which there are 2 points existing that cannot be used as reference points for Taylor expansion. So I told you that these 2 points, you can compute the derivatives in them of any order, first derivative, second derivative, any order derivative, but they all will be 0. So if you try to use each of these points, -1 and 1, in the framework of real calculus as reference points for Taylor expansion, then you are not going to be able to produce this cap-like or bell-like function from these points, because all the derivatives are going to be 0, and the function that also satisfies such Taylor expansion is just 0, constant 0, with no this cap bump in the middle. So real functions apparently may coincide together in certain points up to all derivatives, up to all orders of magnitude, all orders of approximation. So this function here coincides with the constant 0 in these points. But in case of complex functions or functions of the complex variable, it's not the case. If a function is differentiable, it is uniquely differentiable, and its Taylor expansion exists, and it's differentiable as many times you want. It cannot have just fixed number of derivatives. It always has all derivatives all the way to infinity. All the derivatives of all order, of any order. In particular, what happens with this function when being expanded into the complex domain, one can just prove that in the I-axis, these points are not longer well defined. The function diverges in them. If you approach these points not along the real axis but along the imaginary axis in the direction of I, the function will just diverge. you cannot compute a solitary value to this function. Therefore, these points cannot be used as reference points at all. Not because the function will coincide with zero, constant zero, but just you cannot use them because the function is not defined there. Useful property, and in a way it erases an unnecessary ambiguity. We want the Taylor expansion to be unique to every function, and it's a great luck that complex numbers provide us with such opportunity. The link between exponential and trigonometric functions is shown here. It's a famous formula called Euler formula. Leonhard Euler is a great Swiss mathematician who spent lots of time working in St. Petersburg in Russia. Of the 18th century, I guess there are no fields of mathematics of that time where Leonhard Euler hasn't obtained any strikingly good results. Right now, even lots of mathematical objects are named after him. So this is one of the formulae that he derived, and it says that the number e, which is also named after him because his surname starts with e, so this number e raised to the power x plus iy can be represented as a combination, as a product of an exponential function, a trigonometric function of different arguments. The real part of this complex number just goes to the exponent, while the imaginary part, the part proportional to I, when being, exponentially transformed, just turns to the sum of cosines and sines, with I being multiplied to the sine. It's a beautiful formula. We have learned something about the exponential function in the previous lecture. We have learned something about trigonometric functions. But this formula really allows to study both of them in a framework of each other. It can be extremely powerful and extremely useful. And for example, it is useful in the analysis of radio waves and signal encoding and signal to noise ratio improvement, denoising, smoothing, whatever. The fourth advantage of complex numbers is that the space of complex numbers forms the broadest extension of the space of real numbers, which is still a field. And by saying a field, I don't mean here a vector field, as discussed previously. I rather mean the algebraic notion of fields, which is a completely different concept, coincidentally named the same way as the vector field, and it does generate some ambiguity. But anyways, in algebra, a field is essentially just the space of certain objects, numbers in our case, in which the intuitive properties of arithmetics still hold. So that the multiplication and addition is commutative, that you can move some factors outside the parentheses, that you cannot divide by zero, such obvious rules, non-contradictory to our common sense, hold for complex numbers. But if you want to extend it even further and make it, let's say, not two-dimensional but four-dimensional, some of these intuitive rules will break. And once again, I'm not saying right now that these rules will break in case of multidimensional real spaces. Previously, we introduced multidimensional real spaces. With them, everything is fine. For them, we already discussed the framework in which we can work with them. As well, one can generate multidimensional complex spaces with just several copies of the capital C sort of stacked together. No, I'm talking about the algebraic extension right now in the fourth point of this list. I am essentially saying that if you aim to consider not two independent units that multiply to each other in a strange way, but let's say four independent coordinates with also such a convoluted entangled multiplication, which turn to one another when being multiplied to each other. If you try to extend this concept from 2 to some higher number, then you're gonna have problems with the axioms of arithmetics. Then at some point you will not be able to compute multiplication, so the result of multiplication will depend on the order of the factors, or something else will break. In order to study deeper, I refer you to this Wikipedia article. It's called Frobenius theorem. It is discussed there. So in this sense, mathematicians like the space of complex numbers because it's the broadest option how they can extend real numbers and how they can generalize real numbers without losing important properties of them. And mathematicians like to generalize things. On this, I think we're done with complex numbers. And the last topic for today is going to be dot product in general, as I promised. So previously we introduced dot product as the following formula, as I'm pointing right here. However, it holds only in Cartesian coordinates. In other frames of reference, it may not hold, and for other input variants than just numbers, it also may not hold. In order to define dot product in general, we must demand those three axioms to hold together simultaneously. First of all, a dot product is always a number. It's a number, maybe a complex number. So if you flip x and y, then their dot product will turn complex conjugate. Here x and y can be quite well. It can be pretty much whatever. It can. We have a great flexibility of applying the notion of dot product to multiple different vector fields, vector spaces. It can be the space of real numbers, multidimensional real numbers. It can be multidimensional complex space where x and y both have several components, and each component is itself a complex number with a real part and a imaginary part. It can be written in curved coordinates, regardless. So these three axioms are quite flexible with respect to the input to them. So first axiom I already discussed. The second axiom is that dot product is linear with respect to each of its arguments separately. If you substitute x with a weighted sum of two other vectors, x1 and x2, then you can just split the dot product into the weighted sum of the corresponding dot products. Here x1 and x2 are different vectors of the same kind as x itself. Lambdas are the numbers, and realize please that this linearity property is defined for the first argument for x. However, if you want to apply it to y, you will have to first convert x times y to y times x according to the first property. It's also linear, but with the complex conjugation coming in play. And thirdly, dot product is always non-negative when so how to say it, dot square, the dot product of a vector with itself is always non-negative. X times x is always non-negative, and it is zero just in one case and only in one case, when x is zero itself. So when you demand these three, when you find an operation for which all these three axioms are satisfied, then this operation can validly be a dot product. That's what I want to say. Examples. So here are two vectors, x and y. And by the way, once we entered this science of curved spaces and dot products, we will enumerate the components of the vectors as superscripts, not as subscripts. It's done for technical reasons. I'm not going to really dive into it right now, but just remember that these little numbers here are not powers. They are indices of the vector's elements. So here is the Cartesian definition of dot product, which else formulae satisfy the axioms that we previously introduced, the axioms of dot product. Well, instead of just multiplying the first and the second components of the input vectors together and adding the result, we can multiply the components in different combinations and then sum the results, as here. The first components, the first and the second component, the second and the first components, and finally the two second components. And also we want to multiply each of these products by certain number g's with sub-indices. Here we use sub-indices, not superscript. There are some constraints on g's. I'm not going to really discuss it. They should not be arbitrary. First of all, they should be symmetric with respect to the order of sub-indices, but also some other features must be satisfied. And actually, and then each of these triple products has to be summed together. And actually here there is another example of how matrices are used, because G with the sub-indices is also a matrix, obviously. The first sub-index ranges from 1 to 2, and the second sub-index ranges from 1 to 2. But it's not a linear operator anymore. This matrix represents something else. This matrix represents a certain little machine that takes two vectors as an input and returns a number. So just yet another way of using matrices. And finally, to make things yet more convoluted, we allow the g's to depend on the points in the space in which the vectors are actually evaluated. Assume that both vectors x and y are not just fixed vectors, but they are vector fields, and they are evaluated in the same points m. Then, in order to compute their dot products in the given points m, we use the matrix G evaluated in the points m. If we shift a little bit, there can be another value to some of the elements of G, or to all of them. And the way how G behaves, how the matrix G behaves, actually encodes how curved the space is. Here G is one, here G is another, and it essentially, encodes the curvature or the structure of this space locally. It's important to demand that both vectors are growing from the same beginning point. If they are not, then we have to apply the modified procedure of a parallel transform to one of the vectors, just to combine their beginning points, to be able to compute their sum, their difference, and their dot product. The procedure of parallel transport in case of curved spaces is quite tedious, and it also relies on G's. The matrix G is called the metric matrix here. Metric matrix. That's it. Yet a little bit more to be said on dot products, and I will give you a more specific example how to compute it and what it actually means. So here is the formula from the previous slide, just in a more compact way. G sub k comma s is a metric. These guys are the components of the vectors. The summation affects the indices ranging through all the values from 1 to the dimensionality of the space. How to visualize it? Well, first of all, there is a formula of how to construct the metric. Assume that previously there were Cartesian coordinates x sub 1 all the way to x sub n, and we converted them into the curved coordinates just the same way as we converted Cartesian coordinates to the polar coordinates using some nonlinear formulae. And the inverse formulae are representing the old Cartesian coordinates as functions of the new curved coordinates. So that's the formula. Let's compute the matrix of the first derivatives of these functions. The derivative of old coordinates with respect to the new coordinates. Old straight coordinates with respect to the new curved coordinates. This matrix is called a Jacobian matrix. Assume that it's non-degenerate, meaning that its determinant is non-zero. In this case, the matrix can be assembled from Jacobian matrix using this formula. It's going to be the product of the transposed Jacobian and the Jacobian itself. Here is an illustration how it all works. Assume we have a nonlinear space, a surface. It's depicted here. It has its own frame of reference, those little facets, they represent the internal coordinate grid of this curved space. There are two vectors in the points M, A and B, which are no longer formally in the surface itself because the surface is curved, but they are tangent to the surface and they can be validly operated in the framework of dot products and stuff. How can we compute the dot product between these two vectors? We can do it two ways. We can either introduce a new set of coordinates, the Cartesian coordinates, x and y and z, represents these vectors a and b in the Cartesian coordinates, like they are shown here, move them to the origin using a regular parallel transform specified for Cartesian coordinates, and computes the dot product just based on its definition, Cartesian definition. Great. Alternatively, we can imagine ourselves as being little ants, little insects who live only on the surface and have principally no ability to just expand into the three-dimensional space. And what can we do in this case? Well, in this case, we mathematically also compute the three Cartesian coordinates as the inverse functions of the function that defines this curved space, and it's shown here. So we compute the Cartesian coordinates from the curved ones using this formula here and the Jacobian matrix. We compute the matrix. We compute the metric matrix, and then we compute the dot product between those two vectors within this curved space according to the formula for the dot product with the given metric. And those two results will be the same. Those two operations will give the same results. We can either expand our attention to the three-dimensional Cartesian space, Euclidean space, move the vectors to the origin by parallel transfer and multiply them there, or we can introduce this complicated metric matrix in the curved space itself, multiply those two vectors using this metric, and the result is going to be the same. So all these approaches are very much used in the modern theory of gravity, in the theory of relativity, because you all know probably that our space-time is warped. It's non-Euclidean. Gravity, mass and matter and energy affects the metric of our space-time, and since we cannot just easily expand our attention to a Cartesian space of higher dimensionality as here, we also live in a curved space-time. The only way how we compute dot products between our vectors in case of cosmology, strong gravity fields, and etc. The only way to compute dot products in this case is to construct the metric and use it. Further, all these questions are brilliantly, absolutely brilliantly explained by Leonard Susskind on YouTube. He's a professor at Stanford University and a fabulous narrator. All right, I guess for today it is done. I'm pretty exhausted, but you are doing a great job as well. You're doing very, very well. Let's continue our discussions, and I guess the next topic we're gonna touch in the next lecture is going to be differential equations and dynamic systems. On this, all the best, everyone. See you at some point.